Section 4.1, real vector spaces. I had given somewhat of a brief introduction on last time. We want to be able to show that certain sets are indeed a vector space here, a real vector space, by showing 10 axioms. The first 5 pertain to vector addition. The last 5 pertain to scalar multiplication. So if we're given a problem, the problem is then asked, does this set define a real vector space by indeed showing the 10 axioms? And so let's look at that. The first 5 indeed deal with what we say to be is vector addition, that a vector space, some arbitrary non-empty set here, V is said to be a vector space defined with vector addition, scalar multiplication, where we suppose that there are certain vectors that exist within the space, U and V and W, and then some number, some scalar. Here we claim 2 scalars, K and M are real numbers. If these vectors satisfy all 10 requirements, then we say that the space is indeed a real vector space. I've labeled, just for notation purposes, A1 to A5, which reflect vector addition, and then M1 to M5, which reflects scalar multiplication. The first one, A1 and M1, deal with the closure property, that the items within the set or the space must be all contained. So here, if we're adding vectors, the result of the vector must also be within the space. And that's the closure property for addition. The associative property, very straightforward, that things tend to collect together that are alike. That's the associative property, whether it's philosophy, psychology, or anything, just in nature, like terms tend to attract each other. The commutative property, very standard, you've seen that before. A4 is the so-called zero property that we call the additive identity property for addition. Here, that a vector plus a 0 has to equal that original vector. A5 is the negative property, that if there exists a vector, does its negative translation also exist, such that the vector plus its negative has to equal the so-called additive identity. So we have the additive identity, which is 0, and then you have the additive inverse, which is here the negative of a particular vector. Then you go to 6 through 10, that is M1 to M5. M1 is the closure property for scalar multiplication. If I have a vector, if I multiply a number, a scalar to that vector, does it offset the vector definition? Is the result of the scalar times the vector, is that still contained within the space? We call that the closure property for scalar multiplication. M2, M3, here both deal with the distributive property. One is the distributive property for vectors, one is the distributive property for scalars. That is, that if I distribute a scalar on a sum of vectors, is the result true from the left side to the right side? We have to show all of that. And then M3, can you distribute here a vector over the sum of scalars, and is the result to be the same left side to the right side? We have to show that. So you have distributive property for scalars, distributive property there for vectors. M4, the associative property for scalars. And so very straightforward. We'll look at that. And then number 10, or M5, is the multiplicative identity property. And that's called the element 1. Is 1 times a vector? Does it offset the vector? does the vector stay the same? Well, hopefully it does. Well, sometimes it may not, and we have to see all of that. Well, let's look. So take this first problem. Show whether or not the following set defines a vector space by verifying each of the 10 axioms. Let V be a set of ordered pairs of real numbers with vector addition defined as the standard way. There, two vectors u plus v, where u is u sub 1 and u sub 2, and v is v sub 1 and v sub 2. When you add those two vectors, you simply add the components. With here, scalar multiplication defined as k times u, which here, according to that definition, it's 0, comma, k times the second component for the vector. So we want to show all 10. So we first begin by saying let u, v, and w be within this set of vectors. We need three vectors, especially to show the associative property. And let, I'm going to use k and l here, be scalars. So first we take m1. So let u and v be within this big space. Then u plus v, which is u sub 1 plus v sub 1, comma, u sub 2 plus v sub 2, is also within the space, because that's based on its definition, straightforward. A2, the associative property. So here we let u, v, and w be within this space. Here, to show that u plus v, with emphasis there first, plus w, is that the same as u plus v plus w, with then the emphasis on v plus w. Call this the left side, and we'll call this the right side. So for the left side, u plus v, emphasis there first, then plus w, is equal to u sub 1 plus v sub 1, comma, u sub 2 plus v sub 2. Close that up, then plus w1, comma, w2. This is equal to, just according to how vector addition is defined, we just add the components. So here this becomes u sub 1 plus v sub 1 plus w sub 1, comma, this is u sub 2 plus v sub 2 plus w sub 2. Well, that's the left side. What about the right side? So this is u plus, now parentheses, v plus w. So this is the u is u sub 1, comma, u sub 2 plus v plus w is v sub 1 plus w sub 1, comma, v sub 2 plus w sub 2. Now we add them all together and we get equality. So u sub 1 plus v sub 1 plus w sub 1, comma, u sub 2 plus v sub 2 plus w sub 2. So we get the left side The left side is equal to the right side. A sub 3, the commutative property. So here, to show that u plus v is that the same as v plus u. So here, u plus v is equal to u sub 1 plus v sub 1, comma, u sub 2 plus v sub 2. And that will be the same as if we look at that in the reverse in terms of v plus u, that is v sub 1 plus u sub 1, comma, v sub 2 plus u sub 2. That is v plus u. I have not seen the a sub 3 fail with most of these so-called spaces. Typically a sub 2, a sub 3, they tend to follow pursuit. We get iffy once you get to a sub 4, a sub 5. For this problem, since the vector addition here is standard, you won't have any issues there. But the next problem you'll see where some things somewhat looks fuzzy. Okay? So a sub 4, here we want to find the 0 element. I call it theta. I'm going to call it theta because sometimes 0 may not look like 0. So here, to show that for every u that's in this space, there exists a 0 such that u plus 0 is the same thing as 0 plus u, and hopefully that gives us u. Well, I'm going to say directly that this 0 element is 0, 0. Sometimes it's not that easy to see that it's going to be 0, 0, and I'll show you. So here we have u plus theta is equal to this theta, this 0 plus u. This implies that u sub 1, comma, u sub 2 plus 0, 0. That should be the same thing as 0, 0 plus u sub 1, comma, u sub 2. That is to say that here we have u sub 1 plus 0, comma, u sub 2 plus 0, which is equal to u sub 1, comma, u sub 2. That's equal to u. I think it's very straightforward. For the so-called negative A5. The so-called negative. Here we say that for all u that's in the space, there has to exist, if the space is to be a vector space, there has to exist a negative translation of u such that u plus negative u is equal to that 0 element. Well, here the negative element will be just the direct negative translation of the vector. Um, so here this u plus negative u is equal to u sub 1 comma u sub 2 plus, let's say for example, if you don't know what that is, and sometimes you may not, so we'll use generic rigor, simple rigor, negative u sub 1 hat comma negative u sub 2 hat is equal to here 0 comma 0. Well, this implies then that u sub 1 plus negative u sub 1 hat is equal to 0, and u sub 2 plus negative u sub 2 hat is equal to 0. And both implies here that negative u sub 1 hat is equal to this 0 minus negative u, so that's what that guy is, and negative u sub 2 hat is equal to this 0 minus this u sub 2, so negative u sub 2. So negative u here, or negative u hat, is equal to this negative u sub 1 comma negative u sub 2. Again, this particular set of vectors, very straightforward. We get what we call the common or the standard negative. We get the standard 0. Standard 0 for the 2 space is 0 comma 0. The standard 0 for the 3 space is 0 comma 0 comma 0. But sometimes 0 may not look like 0, but another term can act like a 0. That's fine. I'll show you that in the next problem. M1, this is the closure for scalar multiplication. Which simply says that for all u that's in the space, and for all scalar, so k is some scalar, here is the scalar times u. Is it in the space? Well, let's see. This is k times u, and u is u sub 1 comma u sub 2. What is that equal to? This is what? The scalar times that vector. Is 0 comma k times u sub 2. Why is it 0 there for the first component? Because that's how it's defined. Do you see that? That's given information. I can't change that. You can't change it. Most important. If you're writing a computer code, it doesn't matter about what you think things are outside of that code. How information terms are defined at the top of that code is how that code is going to see and try to compute the items within the code. Doesn't matter about what may be real outside of that. You can define within that particular program addition, powers, or whatever. So that if it's Pascal, if it's C++, it only recognizes what's defined in the program. That's all it knows. That's all it knows. That's important. If you're applying for a job, and if the items in that job description says that you must show, demonstrate somewhere in the application, the resume, or whatever, your cover letter, that you have expertise in items A, B, C, and D. And if you don't state that you have expertise in those items, even if the people at that job know that you have expertise in certain things that relate to that, but if you don't state that, your application is kicked out. And then you come back and argue and say, well, hey, I've done this work for y'all before, as a part-time consultant, but yeah, we understand that, but now you're applying for a full-time position, and we state specifically in the description, you must show, demonstrate in your application that you have this experience. You must state it. We can assume that you know it and that we know you. What if there's somebody else from Nebraska who's in the same situation, but we don't know that person, and they don't list it on their application? So is it fair that we give you the job because you didn't state it, but since you worked for us before, we ought to assume that you know it? Here's a person in Nebraska. He has the same experience, but he didn't state his information in the application. We don't know him. We definitely won't give him the job, so why should we do the same for you? Everything must, if it's asked, whatever is defined, that's how you must abide by that particular set of requirements. Here, that's what mathematics is trying to teach us as well. So this is how scalar multiplication is defined by the problem. So now the question is the vector 0, KU2, is that within this two-tuple space, capital V? Yes, it is, because that's how it's defined. This is within capital V. M2, distributive property here for vectors. So is it true that K times U plus V, is that the same as KU plus KV? Well, let's look at the left side. Excuse me, can't say that. This is K times U plus V. This is equal to K. I need to add here, the emphasis for the parentheses simply says whatever is inside, that's what you deal with first. So here we add the two vectors, U plus V. So we get U sub 1 plus V sub 1, comma, U sub 2 plus V sub 2. That's equal to, here now this is scalar multiplication. The scalar times a vector. The first component is translated into 0. This is 0, comma, K, U sub 2 plus K, V sub 2. Now what about the right side? KU plus KV. So this is scalar multiplication, so we deal with that. So this is 0, comma, K, U sub 2 plus 0, comma, K, V sub 2. Now for vector addition, it's the first component of the first vector plus the first component of the second vector, comma, the second component of the first vector plus the second component of the second vector. This is just 0 plus 0. That's 0. Right? Comma, add these two terms, K, U sub 2 plus K, V sub 2. Right? We get equal. The left side is equal to the right side. Okay. And we move on now to the distributive property for scalars. M3. That is, you want to distribute two scalars, K plus L, on a vector. Is that the same thing as K times U plus L times U? Excuse me. So the left side, K plus L U. This is the K plus L which are scalars, times the vector. So this is k u sub 1 plus l u sub 1, comma, k u sub 2 plus l u sub 2. Now what about the right side? Can I squeeze it here? This is ku plus lu. So forgive me. First component must be 0. Here, this is, because this is a scalar times a vector, so this is 0, comma, k, u sub 1, well, u sub 2, that's the second component, plus l, u sub 2. Good. Now watch this. This is k, because that's the scalar. Scalar, k, times this vector, this is 0, k, u sub 2, plus, now l times u, this is 0 times l, u sub 2. Now I add the two vectors. I get 0, comma, k, u sub 2 plus l, u sub 2. They're the same thing. They're the same. So we get the left side is equal to the right side. M4. M4 is the associative property for scalars, for scalar multiplication. So is KL, emphasis there first, times U. Is that the same thing as K? Here the emphasis is on this one scalar times the vector. So let's see. The left side well, this is the scalar multiplication, so the first term is 0. Put the emphasis on the two scalars being multiplied. It's looked upon as being just one scalar times that vector component. So this is KL times U sub 2. On the right side, K times LU. Now this one, you have to take your time and work it into parts. So this is the L times U, which is 0 times L u sub 2. And then it's the scalar k times the vector, which is 0. And then this is kl times u sub 2. So we get the left side equal to the right side here as well. And we got one more to go, but I want to ask this question. Would this space define a vector space? We just got one more to go. We'll do that one in just a minute. But does this space, does it define a vector space? Who was that? Amen, Michael. That's the wisest answer. Okay, good. Spoken like a true mathematician. So, M5 says, is 1 times any vector in that space? Do we get that vector? So 1 times u, do we get u? Well, let's see. Here, this is 1 times u. What's that equal to? 0, comma, u sub 2. Is that equal to? U is what? U sub 1, comma, u sub 2. It's not equal. This is not a vector space. Because of that last property, it fails. You go through all that work, Batista, and you hope that from all that, 1 through 9, this guy better be, It's not. Sorry, Charlie. Right. Yes, sir, James. Yes. problem. Show whether or not that the following set defines a vector space by verifying each of the 10 axioms. Okay. So if a problem says that, you have to show all 10. If it doesn't say that statement, then you can just pinpoint the one that fails, or maybe 2 of them that fails, and then you're done, right? Yeah. I hate that part too, but it's in there. So, oh, what do you say about it, Tyler? Number 2, show whether or not the following set defines a vector space by verifying each of the 10 axioms. Let V be a set of ordered pairs of real numbers with vector addition defined. Did I say at the end? Need to conclude down here, I'm sorry. The set V is not a vector space because axiom 10 fails. So, right? So here let V be defined by the ordered pair of real numbers. Here with vector addition defined as this, U plus V is U sub 1 plus V sub 1 plus 1, comma U sub 2 plus V sub 2 plus 1. And then scalar multiplication is standard, right? So the only twist is going to be on the vector addition. Okay. So we start with A1 with the closure property. For addition, and put the let statement here. Let U, V, and W be in this big space, and let K and L be scalars. So here, U plus V, which is defined here as U sub 1 plus V sub 1 plus a 1, comma, U sub 2 plus V sub 2 plus a 1. This guy is indeed in this space because that's how this space, or this set, these set of vectors are being defined. So that one is good. So A2 is interesting in terms of the associative property for vector addition. Let me work it out, then I ask the question and see if you see what's happening. Here to show that U plus V, with the emphasis on U plus V plus W, is that the same thing as U plus, here the emphasis is on V plus W. Okay. So look at the left side. U plus V in parentheses, then plus W. So this becomes U sub 1 plus V sub 1 plus 1, comma, U sub 2 plus V sub 2 plus 1. Close that up. Plus here, this W, which is the W sub 1, W sub 2. That's equal to U sub 1 plus V sub 1 plus W sub 1 plus 2, comma, U sub 2 plus V sub 2 plus W sub 2 plus 2. Basically what it says is that if you add two vectors, you have to add a 1 to that. So here, I've added these two vectors, U and V, and I have a plus 1 there, but now I'm adding the U plus V plus the W. So here I'm adding a 1 to that as well. Now look at the right side. So this is u plus parentheses v plus w. So here this the u is u sub 1 comma u sub 2 plus the v plus w is v sub 1 plus w sub 1 plus 1 comma v sub 2 plus w sub 2 plus 1. And we add them both together. We get u sub 1 plus v sub 1 plus w sub 1 plus 2 comma u sub 2 plus v sub 2 plus w sub 2 plus 2. My question here is, does A2, does it fail or does it satisfy the requirement? It satisfies it because the left side is equal to the right side. That's the key, right? We get equality. It looks like, based on the definition, if two vectors are added, there's a 1 added within the components, right? Here I'm adding 3 vectors. So it's, if you look at u plus v, right, I'm adding a 1. And then the u plus v, look at that as being 1 vector. Plus w, I add a 1 there as well, right? But the emphasis here is that the left side equals the right side, so this axiom holds. A3, the commutative property, u plus v, is that the same thing as v plus u? Well, this implies, here I'm going to write the left side equal to the right side. We get equality here, everything is fine. U sub 1 plus v sub 1 plus 1, comma, u sub 2 plus v sub 2 plus 1. This is indeed the same thing as, look, once the vectors are added, the subcomponents within the vectors are just numbers. And those numbers satisfy the regular set of real number operations, just like adding 5 plus 2. That kind of thing. So 5 plus 2 is the same thing as 2 plus 5. You can switch them, and that's okay. So here, we can say this is the same thing as v sub 1 plus u sub 1 plus 1, comma, v sub 2 plus u sub 2 plus 1. Well, this is the same thing as v plus u. So u plus v is the same thing as v plus u, and that's fine. Now, what about a sub 4? A sub 4 is on the 0. So here, for every u that's in this space, there exists a 0, right? A 0 such that u plus 0 has to equal to u. Well, let's see. So here u is this u sub 1 comma u sub 2. Plus this 0, I'm going to call it theta sub 1 comma theta sub 2. It has to equal u sub 1 comma u sub 2. The only problem is that when you're adding vectors here, you have to add a 1 component within the categories of the components, right? So the left side is u sub 1 plus theta sub 1 plus 1, comma, u sub 2 plus theta sub 2 plus 1. That has to equal to u sub 1 comma u sub 2. Well, the only way to rectify that is this. If you look at it, this implies that u sub 1 plus theta sub 1 plus 1 is equal to u sub 1, and u sub 2 plus theta sub 2 plus 1 is equal to u sub 2. Well, that implies this, that theta sub 1 has to equal to negative 1. And theta sub 2 has to equal to negative 1. Do you see that? All right? Solve for theta sub 1 here. Subtract u sub 1 on both sides. Subtract 1 on both sides. I get theta sub 1 is equal to negative 1. Same thing for theta sub 2, which implies that the 0 for this particular set is negative 1 comma negative 1. Negative 1 comma negative 1 acts like a 0. Okay. So here you check it. So u plus theta, we say here has to equal to u. That is u sub 1 comma u sub 2 plus negative 1 comma negative 1. That's equal to u sub 2 plus negative 1 plus 1 comma, that's u sub 1, that is, comma u sub 2 plus negative 1 plus 1. Well, that's equal to u sub 1 comma u sub 2, and that's equal to u. Right? So indeed, this is a proper negative. Well, this is a proper 0, excuse me. This has the negative ones in it, but that's the 0. We're looking for the 0. Now here, we look for the negative. The negative, right? So here, for every vector u within this so-called set of vectors, there has to exist a negative u such that u plus negative u has to equal the 0. So here we have the u, which is u sub 1 comma u sub 2, plus this negative, so we call it here negative u sub 1 hat, comma, negative u sub 2 hat. We don't know what it's going to be. It has to equal to negative 1 comma negative 1. So this implies then that u sub 1 plus negative u sub 1 hat plus 1 equals to negative 1. And the other component is u sub 2 plus negative u sub 2 hat plus 1 has to equal to negative 1. Now all that implies, let's take that first part here. We're going to solve for the negative u sub 1 hat and then also solve for the negative u sub 2 hat. So here, negative u sub 1 hat is equal to negative 2 minus u sub 1. And, yes, negative u sub 2 hat is equal to negative 1 minus u sub 2. Negative 2, excuse me, minus u sub 2. Looks like a W. So that implies that here, for each u, negative u is defined as negative 2 minus u sub 1, comma, negative 2 minus u sub 2. You can check it, it does work. You see what I mean? That it's possible that 0 may not look like 0, but it acts like a 0. The negative of a vector may not look like the standard negative, but it acts like a negative. And that's the key. Okay? Any questions? There? Yes, sir. Daniel? Okay. Yes, sir. If you solve, remember, once the terms are applied to the components, where it's like the parentheses and stuff inside, those terms are now just regular numbers, and I can treat them as such. And with regular numbers for the real number line, I can add and subtract, with respect to the number line. So I can add a number, I can subtract a number. So if it's an equation, you can solve an equation, you can subtract the same term on both sides. So for this negative u sub 1 hat, how do you get that term by itself? I'm going to subtract u sub 1 on both sides and subtract 1 on both sides. So I get negative 2 minus u sub 1. Right? And the same thing for the negative u sub 2 hat. Okay? Now, m sub 1, the closure property for scalar multiplication here, if u is in the space and k is a real number, then k times u, which according to its definition of scalar multiplication is standard. It's standard. So here, this is k u sub 1, comma, k u sub 2. It's in the space, so we're fine there. And that's just straightforward with respect to the definition. So m sub 2, the distributive property here for the vectors. So if we have k times u plus v, is that the same thing as k times u plus k times v? Well, let's see. Look at the left side. K times u plus v. So we first put the emphasis on what's inside the parentheses. So this is a scalar on the outside. I'm going to add those two vectors. This is u sub 1 plus v sub 1 plus 1, based on its definition, comma, u sub 2 plus v sub 2 plus 1. Then we multiply by the scalar. The scalar multiplication is standard, so it's k times each term, each component, right? So this is k u sub 1 plus k u sub 2 plus k, comma, k. Okay, that's u and v. V sub 1. And this is plus k v sub 2 plus k. Now the right side is ku plus kv. We first have to deal with here, this is scalar multiplication. So this is k u sub 1, comma, k u sub 2, plus k v sub 1, comma, k v sub 2. Now I add two vectors based on how vector addition is defined up above. So this is k u sub 1 plus k v sub 1 plus 1, comma, k u sub 2 plus k v sub 2 plus 1. The left side does not equal the right side. Right? So we keep moving. M3, because the problem here says you must show all 10, right? Whether each one fails or holds, you still must state. So we just can't stop and say, okay, this one fails, it's not a vector space. Well, that is true, but here the question asks to show all 10 axioms. Right? So M3, the distributive property for the scalars. So here we have k plus L, two scalars, times a vector. Is that the same thing as k times u plus L times u? Well, let's look at that in pieces. The left side, k plus L times u. So here we treat the scalar, k plus the scalars, k plus L, as a scalar. So it's going to be a scalar times the vector. And so the vector scalar multiplication, was defined by the standard way. So this is k u sub 1 plus L u sub 1, comma, k u sub 2 plus L u sub 2. And what about the right side? This is ku plus Lu. You can kind of see very similar to the previous axiom in terms of how things worked out. Before you add, I have to deal with the order of operation of multiplication. Multiply the scalar times the vector. So this is k u sub 1, comma, k u sub 2 plus L u sub 1, comma, L u sub 2. So now I add the two vectors. I get k u sub 1 plus L u sub 1 plus 1, comma, k u sub 2 plus L u sub 2 plus 1. So here indeed the left side is not the same as the right side. M4. M4 was the associative property for scalars. So is k times, this would say k times L in parentheses first. Is k times L in parentheses times u. Is that the same thing as k times in here with emphasis on L times u? There was no trouble with the scalars. So the left side, k times L times u. This is KL u sub 1 times KL u sub 2. And notice here that even if you pulled out the k and you had what was left, L times u sub 1 comma L times u sub 2. That's here. This is k times L u. So the left side does indeed equal the right side. M5, saying 1 times a vector, does that give us the original vector? Well, let's see. 1 times u is 1 times u sub 1 times u sub 2. Is the standard definition for scalar multiplication is the scalar times each term inside the components there of the vector. So this is 1 u sub 1 comma 1 u sub 2, which is equal to u sub 1 comma u sub 2. That's equal to u. Right? So M5 holds, but notice that M2 and M3 failed, so this is not a vector space due to that. So let's say V is not a vector space since M2 and M3 failed. Well, let's keep digging here. Here, number 3. Since my time is going to be limited here, we got 14 minutes, and I got numbers 3, 4, I think 5. I think that's it. Oh, there's number 6 there. Oh, there's number 7 as well. Okay, let's see if I can work 3 of these by just kind of gleaning over them. Number 3. Number 3 says that the set of all pairs of real numbers of the form x comma 0 with the standard operations on R2, that's the 2 space. This set is a vector space. Okay? It satisfies all 10. Basically, all the vectors of that form. So if you think ideally, all the vectors with the first component and the second component is 0. If I add vectors like that, is the result the same? Yes, it is. If I multiply a scalar times this vector set, is that result the scalar times a vector? Is it still first component comma 0? Yes, it will be. So this set is a vector space. It satisfies all 10. And let me go ahead and just state the critical items. What's the 0? What's the negative? That kind of thing, right? So here, the 0 vector is, now it's okay if that first component is 0 for the 0 vector. The 0 vector is that because here x comma 0 plus 0 comma 0 is equal to x comma 0. Right? The negative for vectors of the form x comma 0 is negative x comma 0, which implies that x comma 0 plus negative x comma 0 is equal to the 0, 0 comma 0. Right? The 2 key axioms, A1, let x comma 0 and y comma 0, they don't call this space by any title. I can say it's in R2, that's fine. Say here, it's in R2. Well, x comma 0 plus y comma 0 is equal to x plus y comma 0. That's still in R2 of the form, right? And of the form x comma 0. And then the last one that's critical is M1. And I'm going to show you how important A1 and M1 are, because I think it's the next one, and go ahead and show you that the next one fails and just pinpoint it. Now, indeed, they want you to show all 10, but my time is limited. I kind of want to just let you see, what's happening. Here, M1, the scalar multiplication closure property. So here, just let u equal to this x comma 0. It's in the 2 space. And k is any real number. So k times u is equal to kx comma 0. It's in the 2 space. It's of that form, x comma 0. That's good. This sets a vector space. Now, number 4, my question to you is this set of pairs of real numbers of the form x comma y, where the first component is positive with the standard operations in R2, is that a vector space? No. And the reason why? That's right. That's good. Yeah. Because if that be the case, then the negative wouldn't even exist, right? Very good. Very good. You're thinking deeper than me. This set is not a vector space. Now, watch how I classify this, James, because M1 fails. Do you see that? Because remember, look, the scalar k can be any real number. It can be negative. Right? So here, if u is equal to x, y, where the first component is positive, and k is any real number, suppose k is negative, because the scalar can be negative. It doesn't have anything to do with the vector x comma y. So if k is negative, then k times u, which is kx comma ky, the first component would be negative. Do you understand that? An example. say u is equal to 5 comma 3, where here, look, the key is that 5 is positive, right? That's what they stress. The first component is positive. Take k to equal to negative 2. It doesn't matter. Any negative number is fine. Say negative 1. Then k times u is equal to negative 1 times 5 comma 3, which is negative 5 comma negative 3, right? Which is, this guy is not, this is not in the defined space. Because the space is here is defined as being a two-tuple where the first component must always be positive. Right? So that doesn't hold up for closure, because you can multiply a negative scalar times that vector, and the result will give you that first component to be negative. Right? Let's see. Let's do this one, and then I'll wrap it up. The set of all 2x2 matrices of the form here with the standard matrix addition and scalar multiplication. With these sets of matrices, would they form a real vector space? Stephen? With this number 5, is this a vector space, or is it not a vector space? I do suppose that what you have on your computer does pertain to what we're doing right here. Is that correct? Stephen? Okay, no, it is a vector space. It's a vector space. Why wouldn't it be a vector space? If you have vectors of this form, so if you add them, would the resulting matrix be of that same form? Let's see. Let A equal to A0, 0, B, that's fine. Let the matrix B be C0, 0, D. So the first property, A sub 1, says that when I add these two matrices, is the resulting matrix still of that form? Yes. A plus C, 0, 0, B plus D. It's still of that form, right? Yes. A2, A3 is satisfied. A4 for the 0 matrix, the standard 0 matrix for 2x2. A5, the negative. If A is equal to A0, 0B, then negative A is equal to negative A, 0, 0, negative B. Right. It's going to be the standard negative for this type matrix. M1, if you have a scalar times that matrix, does that scalar offset The matrix type, the matrix result? No, it doesn't. This is going to be KA00 KB. Yes.
Unless it says otherwise, we should assume that it's going to be standard for anyone as far as k times a, it's not going to be some strange rule like we had in the first example.
No, because here it says with standard matrix addition and scalar multiplication. Yep, yes, sir. That's exactly what that means. Right? So all the critical components are satisfied. Here's the other critical component would be M5 is 1 times the matrix. This is 1A, 0, 0, 1B. That's equal to A, 0, 0B. That's equal to A. This set of matrices forms a vector space. Okay? Any questions? Yes, Stephen. Right, because you got the number 5, it's going to throw off. 0 is fine, because saying 0 plus 0 still gives you 0, right? When you add 5 plus some other number, does that still give you 5? It does not. Right? That's different, right? 0 is always good, because when you add to that 0, it doesn't offset the vector term, right? So u plus 0 is still going to be u. Yes, sir. If they replace the zeros with a 5, and would that set be a vector space? No, it would not. Right? Because saying some scalar times 5, that's going to give you not 5 anymore, right? The scalar, say for example, if the scalar is 3, 3 times 5 does not give you 5 anymore, it gives you 15. But k times 0 still gives you 0. Right? It's a big difference. Yep. Okay. Do the homework for this section, and I'm going to put today in Blackboard, and should also shoot an email to you how we're going to finish this course for the duration of this semester and what I'm going to cover each day. Okay? Thank you.